cover slide right now.
Yeah, we can see that.
Yeah.
So welcome you all, and very good morning, Professor Constantine Megaridis from University of Illinois at Chicago. So Professor Megaridis received his PhD in fluid thermal science from Brown University, where he holds the MS in applied mathematics. He is a fellow of APS, ASME, and he received many awards, teaching and research awards, including UIC Distinguished Professor Award in 2018 and UIC Inventor Award in the year 2015. Professor Megaridis works on different fields in thermal and fluid sciences, including fluid particle transport, multi-phase heat and mass transfer, multifunctional coatings and interfacial phenomena in micro and nanofluidics. So I will ask Professor Megaridis to start his talk. This is our third talk in the MNBF Talk Series, monthly talk series. So welcome, Professor Megaridis, again in our talk.
Thank you, Palab. First of all, my thanks to all of you who extended the invitation, and Palab in particular, my former colleague here. And I see this as the pretty much the only benefit of this pandemic era, where we can actually connect from all corners of the globe and do what we love best, science and engineering. And I'll describe today a cross-section of many things we do in my lab, which is called Micro Nanoscale Fluid Transport Laboratory. And this is something that is particularly related, of course, to what you are trying to do there, in the sense that the theme of your center or your group is microfluidics. So today I will describe some of the let's say general descriptions of studies that we do here in microfluidics, and then go on to some energy applications, again, that involve the transport of fluids at the microscale, and then give some ideas about what could be done beyond those areas, because these are not the only ones, of course, that one encounters the interaction of fluids and solids, and of course many technologies that are out there, ranging from energy and water, the nexus itself right now, which is pretty much at the center around the world, and many other technologies, microelectronics and cooling, for example, power electronics, electronic vehicles and electric vehicles, and so on. So the general theme, as I said, is microfluidics, but not only, and the scales that I'm going to today really present. Here we have some things natural at the scale that you see, centimeter all the way down to the nanoscale. Things man-made, again, machines and systems and so on, that are built molecule by molecule, all the way to larger things. But still, the range that I'm going to be talking about goes from nanometers to a few centimeters. So that's the scale then that we're going to concentrate today. So the outline of what I'll present to you in the next 40 minutes. I'll give you the motivation and importance of our work, some definitions. I don't want to preach to the choir here, tell you a little bit about wettability, repellency, wetting states, and so on. I am going to actually keep that very brief, and then go specifically into applications, lab-on-chip microfluidics, condensation, heat transfer, a lot of the work that Dr. Mahapatra, of course, has worked when he was here in the lab, some liquid jet cooling applications, something that was done by another PhD student who's now in industry, and then wrap up with an example of thermal management, something that is related to microelectronics, power electronics, and so on, a vapor chamber, which is a heat spreading device. I'll summarize and of course, list the people who have done much of this work in the laboratory. And just to give you the background here about the effect of wettability, which is really the affinity of a solid surface to be wetted or covered by a fluid, is indicated here. This affinity is quantified in terms of the contact angle, which you see here. If you have a small volume of fluid and you let it sit, this is the sessile contact angle, we call it. The equilibrium angle that is formed at the triple phase contact line, liquid, gas, and solid, designates the wettability of the surface. Small values of theta indicate a high wettability. Large values of theta, in the sense that you have a ball, a basketball, let's say, sitting on top of the surface, large value of theta, that indicates low wettability. So for low values of theta or high wettability, you see when you actually have a small amount of fluid, a droplet in that case, impact on the surface, the outcome is this. If you go to let's say, neutral wettability, where you have theta about 90 degrees, and you do the same thing, nothing else changes, the same liquid, in this case water. The only thing that is changing here is the wettability of the surface. You see the outcome to be quite different. And it's even more drastic when the wettability of that surface is very low. You have this bounce back and eventually the rebound and the multiple events of that sort. And you see how really important is wettability of the surface. And although the kinematic conditions are the same, Reynolds and Weber number and so on of the droplet upon impact are the same, the outcome is quite different. So let's see here how you can use this different, let's say, behavior of liquids when they encounter solids to do certain processes and create certain outcomes that are useful in microfluidics or energy applications and so on. So I'm going to talk about open surface microfluidics. This is our area of expertise here. And I understand a lot of that is also happening at IIT Madras in your group. And we're going to concentrate particularly on pumpless rapid fluid transport. Pumpless from the sense that it's not gravity driven, and rapid in the sense that it's not centimeters a second, but it's rather is of the order of tenths of centimeters a second, up to half a meter a second. So these are almost like convective velocities that are caused by manipulating wettability on a surface. Now, when you look at how a small droplet, let's say, sets itself when we place it at the start of a wedge track, in that particular case, we have a triangular wedge track. We're looking down on this droplet, so this is a top view, and this dashed lines here indicate the wettable domain, and everything else outside is a non-wettable domain. The droplet itself, because before it actually assumes this shape, is of the order of about 2.5 millimeters. This is, on the below the capillary length of water. And why is that important? Well, when we have volumes with characteristic scales below the capillary length, gravity is not at play, or at least it's not important. It may be present, but not important. So as we release this droplet on the narrow end, this droplet is in fact experiencing a force that is pushing it from the narrow to the wide end. And I'll go and specifically into why that is. When you look from the top, again, you have this contact line forces, and because the droplet itself is spilling over and then forming a cross section that looks like this, because of the shape, you have a composite force that in fact pushes the droplet from the narrow to the wide end. And of course, when this configuration here, this cross section becomes that. Things are slowing down because the forces are in the opposite direction and so on, and then hemi-wicking also becoming important. So overall, the droplet that you deposit on a wedge track that is wettable and it's surrounded by a non-wettable domain is being pushed from the narrow to the wide end. And when this analysis, kind of a back of the envelope type of analysis, when you look at how this pressure gradient along X, this is the direction of propagation here, it varies with the surface tension of the liquid. The average contact angle that is formed by the fluid that is spilling over here, the contact angle at that contrast area here, the wettability contrast area. Alpha is the angle of the wedge, and delta, depending on exactly where, at what X you're at, is the width of this track. Now, of course, you see that there's a competition. If you go and you want to do, a larger, for example, to cause a larger dpdx, you need a larger alpha. But when you do the larger alpha, then delta is working against you because it's in the denominator. Remember, a bigger alpha here, if you open that angle, would cause a larger delta, which then, of course, because it's the denominator, it's going to drop this. So it's an optimization game between contact angle. Let's say the surface tension is fixed in that case, between alpha, the wedge angle, and how that delta, the width of the wedge, varies as a function of X. So when you do this and you eventually go through the process of studying the motion of a droplet that is released here with a needle at the narrow end of that wedge, and this is a slow down movement. Gravity here is normal to that plane, so it's not playing at all. And you see this type of movement from the narrow to the wide end. And we need to keep that in mind because it is critical in what I'll be talking about from now on. Now, this type of velocities, as I said, are of the order of tenths of centimeters a second. So these are not velocities, hemi-wicking velocities through, let's say that you will see through a paper towel or a porous medium and so on. Now, what can you do with something like that? Well, this is a depiction of a wedge that now is on an inclined path, and this wedge here, it's depicted when you release it at the narrow end. Because of this force, it will be going upward. You will see that in a minute. And then in this particular configuration, you bring the droplets after releasing them here at the low end all the way up to that pad. And of course, you're starting with energy that is because of the spherical shape and the surface tension of the droplet, kind of a membrane of a balloon that squeezes the interior of that balloon, the contents of that balloon. And as you now allow it a way out, this is the track, this liquid is pushing itself up because of that original excess energy right here. And eventually when it becomes flat right here, that energy has been converted to potential energy, right? You went from here to here. So there's a limit of how long you can raise those. And if you do this simple calculation with a 2 millimeter diameter, again below the capillary length, you can calculate that it can rise up because of this surface energy to about 15 millimeters because of other, of course, losses and so on, friction losses and so on. But the theoretical limit itself is actually 22 millimeters. So about 2 centimeters, but of course you can never achieve that. Now, when you do this and you, let's say you implement that in practice, you have on the left, as you see in this panel, you have the syringe that dispenses colored water. That is dispensed at one point of this inclined ramp right here, this ramp that you see here. And look what happens when we actually start dispensing droplets one at a time. They will start rising and go up here on the pad. And this is what you see here. This is in real time, by the way. This is again red dyed water, and you can see how it rises against gravity. Gravity is pushing down. You see, of course, how the droplet falls with gravity. This contribution, by the way, is very small compared to just a few percent of the energy because of the Laplace pressure in the droplet. And you see how eventually you can get tenths of those droplets up on this pad. So fine, you can do something like that, but you can also do something that is quite a bit, interesting and important for microfluidics. For example, multiplexing. You have one sample, and you want to create multiple, let's say, testing samples from that. This is what is shown here, where you see the droplet at the top is released by the needle. This is again in real time, and you see how this droplet is multiplexed in five-fold. You have these 5 now different samples that you can do different types of, let's say, detection assays that you can have there, and colorimetry that you can use to identify if there are certain chemicals in this droplet. Now, again, as I'm going through the visual part of this, and of course this is not empirical, it's something that has been studied quite extensively in our lab, and you see in all the slides I have the publications at the bottom, and this is a plastic sheet. This is in fact a transparency. In the old times we used transparencies to prepare slides and project them with light projectors and so on. In this particular case, you have these 3 wedges. Two of them are identical here, and by dispensing these 2 droplets one at a time, eventually you can make those. You can make these accumulation points that you see right here. So you dispense the droplets on the narrow end, you go to the wide end of these 2 tracks, and when, after deposition of enough droplets here, this accumulation points become large enough in volume, they merge, and then they actually breach this start point of the 3rd track, and then you have mixing and transport. And this is the final pad where you can do microfluidic detection, let's say, actions, right? Whatever these may be, if you want to detect certain elements or chemicals that are included in either one of those 2 liquids. So let's see then in that particular case what happens when you actually do this in real time. You see the droplets becoming large, they eventually merge together, and it's always happening the same way. And you can see, you can repeat this many times, and you can have, again, gravity is normal to the paper, to the plastic sheet right here, and you see a tremendous amount of fluid that is actually trapped, and that is trapped by the wettability confinement, right? So as we move on, and I want to show you here a slide that looks busy in the beginning, but I'll orient you. This is the schematic of what is in fact depicted here. We have 2 wedges, A and B. A and B, you can barely see them probably. They're a little bit lighter in color than the surrounding. And this is the wettable area. Both A and B are wettable, so A and B are wettable. They extend to the beginning of C, which is this right here. Okay, C, that 3rd staggered track is here. And the interesting part that actually I want you to pay attention to is the presence of this hydrophobic island, which is this one right here. And that hydrophobic island, remember, does not want to be wetted by the liquid. These are, by the way, 2 different liquids, aqueous liquids, both of them. They're salts that react together. And when they react, they create a dark color that shows you the degree of mixing. The higher is the darker is that, let's say, the blackness of the fluid after mixing here, the better is the mixing. So this is qualitatively how we actually evaluate the mixing degree. And these are, by the way, these are millimeters. So this is a centimeter. You're looking at something that is of the order of a few centimeters. Now, as I go to play this video, I want to again point your attention to the left. You see the needle at the top left, and what happens when the droplets here are released, they react. You have the mixing, and you see over the island how the drying occurs. This is drying because of the fact that the surface repels the liquid, and because I'm going to play it again, you'll see some pumping action behind the island, and these wake action is in fact improving the mixing of the two liquids, and the mixing time is far shorter than when you had diffusion alone. So you get the idea, and then you can go and do quite fancy things. In this particular case, I'm going to show you, let's say you have an overpass in this particular fluid. Both of them are water, by the way, a water droplet. We're going to have through this path right here that is kept up by a block right here to go over the path that the green droplet is going through. So you will see, as I play it in just a second, these are, by the way, millimeters. This is 1 centimeter, 2 centimeters here, and so on. You'll see an overpass where the red liquid will go over and the green liquid will go under. And I'm sorry, here it is. Real time. And you bring the green all the way closer to the viewer, let's say, and the red all the way from the right to the left. So you can do either straight paths or curved paths or 3D microfluidic tracks and so on, but you can also do spiral paths. In that case, that spiral is of the order of I believe 20 centimeters or so. So when you actually dispense a droplet right at the after the start, you can see that flash there is the impact of the droplet, and you see how that liquid advances. So there are a lot of things that you can do and manipulate in microfluidics, the kind of stuff that I guess you may be doing there for building devices, and devices that are not particularly applied on one type of substrate, but many different substrates. It can be metal, it can be paper, it can be plastic, it can be glass. Now, as we go on and we look at what you can do with this type of configuration, but when you have non-aqueous liquids, well, in this particular case, let's say that you have an oil, well, you need, of course, to create repellency to the oil, and that's, we all know it's not easy at all. We have a formulation that we created here with collaboration with the US Air Force at Edwards Air Force Base. The group there, the chemists, involves silicon cage compounds, POS compounds, and again, it's not very critical at this point of how we make them, but what is important is you can have also liquids that are non-aqueous with lower surface tensions that actually undergo the same type of movement. So if you, in that particular example, I'm showing you, and you will see that here in a minute, you will see different bands of liquids starting from the top where you have water. The next one is hydrocarbon, I don't remember what it is, maybe kerosene, all the way down to decane, where the surface tension is 23.8 in these units, or dynes per centimeter. And you see really, as you go down to a lower surface tension, it becomes a lot more difficult to repel those liquids. But I'll show you the outcome of this study that again is published, where you have now these tracks. These are slowed down by 10x, by the way. And the tracks from water to hexadecane, kerosene, and dodecane. You see the droplets on the left, and you see how the front progresses to the right, again with droplets with velocities that are quite significant. In this case, up to centimeters a second, up to 10 or even more than that, tens of centimeters a second. So we have recently also been able to create something similar with actually octane, which is in the very low 20s, and to the best of our knowledge, with this type of sprayed coatings and wettability patterns, octane has not been done so far. We're not talking about areas, surfaces that are repelled with highly sophisticated, lithographically made, expensive surfaces. We're talking about something that you can spray and pattern. Now, as we go and we look at the physics of this, if you look at the advancing rate of the fluid, and you see how that actually progresses as a function of time, you see, of course, depending on, this is actually versus viscosity of the fluid, and we did that with glycerol and water solutions. And you see here that the rates, of course, are not the same. However, if you look at what is driving this type of physics and movement, and you look at non-dimensionalization, so you non-dimensionalize the, let's say, the front, the length where, let's say, the front of this droplet is, and with the total length of the track, and then you also scale appropriately the time with respect to the viscosity of the fluid and the surface tension of the fluid. Interestingly, the density is not coming into the picture here, possibly because the density ranges that we looked were not that wide. But what is important here is you have three distinct regimes. You have a hemi-wicking regime right here that Laplace pressure has not yet kicked in. So you have the hemi-wicking of the front. This is the area that is blown up here. Then, and of course, all these now curves collapse in one. This area too, where you have the Laplace pressure actually countered and balanced by the viscous forces, and that's why you have the dx dt here, as you see, to be constant. The velocity is constant. And then you have the third regime right here, where dissipation and viscous forces are taking over, and now you have a dx dt that is much, much lower. So the flow here slows down. Nonetheless, you're able to see that there is a scaling law that you can use, with the exception of density right now. As I said, the density variations we used were not very, very large. They were of the order of about 20 or 30%. But if you go to a scale of, let's say, a ratio of 2 or 3, things may change. Nonetheless, the scaling law allows you for fluids with viscosity, surface tensions, and this type of systems here to predict how a droplet would behave on a wedge if you know what its surface tension is and what its viscosity is and what is the length of the track. Now, the second application is on a non-isothermal case, power density electronics. You're looking at a thermal image of a board that has a very hot, let's say, portion, and then you have other cooler spots. Blue here is indicated by the coolest part of this board, and red the hottest. And of course, how do you maintain this in a way that is safe for the electronics? Right now, there we kind of enlist the physics and thermodynamics of condensation modes. You have dropwise condensation that, of course, is very efficient in heat transfer. Then you have film-wise condensation that is not efficient, but it's good in actually allowing you to remove the condensate. And when you do this, you have the, again, the dropwise condensation, film-wise right here, and you see how the liquid deforms on the dropwise condensation configuration versus film-wise. And because the film is covering the cooled wall, you have in some way the insulation of what is happening on the wall right here from the ambient, and that slows things down. And that's why when you have this and you compare it to this, the heat transfer coefficient for dropwise condensation is far better than the film-wise condensation. So you want this to be able to have efficient dropwise condensation. Now, when you look at how one can achieve that, well, it turns out that when you remove the condensate droplets at lower size, so you don't allow them to become very big, then the dropwise condensation heat transfer is becoming more efficient. And I display here a series of bands of dropwise condensation and filmwise condensation domains. So we have dropwise condensation here, and this is a film, a continuous film of this condensate, water in this case, and it's indicated here. By manipulating and tuning these bands, not in real time, but you do that in advance, you're able now to allow these droplets to become only as large as the width of this dropwise condensation domains. When you do that, then these droplets eventually bridge and they go and they get sucked in by these paths right here. And that's what I'm showing you at this two videos on the right, where you have this is the dropwise condensation and this is the filmwise condensation. So this, I'm sorry, let me again and show you with the laser pointer, dropwise condensation, filmwise condensation. Filmwise is right here, dropwise is right there. And you see, I'll play that in a minute. And the same thing here. Again, this is, you see now the liquid that has been, actually that has inundated the filmwise regime. And this is the dropwise regime. And if I click back to get my cursor back, you will see the two events, how they act to clean up the dropwise condensation domain and generate pristine surface for renewed condensation. Okay, so that of course improves dropwise condensation, and that is achieved by exactly tuning the relative size of the dropwise condensation, which is good for heat transfer, and the filmwise condensation, which is not good for heat transfer but facilitates drainage of the condensate. Now, as we go on, this is work that Dr. Mahapatra actually did in the lab here when he was around. You're looking at this rake kind of patterns. The dark domains are the domains of high wettability, and then when the droplets here in the less fluidic domains, these are the dropwise domains, they get big enough, they get sucked in by these wedges, and then they get drawn into this veins and moved to another part where now you don't have to worry about interfering with the dropwise condensation. This is a sequence here, slow down, that shows you, and this is of course a force situation where we leave a droplet on the end of one of those wedges, and you see how they're directed towards the wide part of the wedge and then the main vein, the vein that you're looking at here. So the strategy here is to use dropwise condensation and filmwise condensation domains to enhance heat transfer. And of course, you got to optimize because one works for you in terms of heat transfer, the filmwise condensation, but the other, dropwise condensation, the filmwise condensation work against you, but the dropwise condensation works for you when it comes to heat transfer coefficient. So in this particular case, you see now this implemented in real application, where you see this popping events, where you have these droplets. When they become large enough, they eventually get sucked in, and they go down this kind of fluid-filled veins, and eventually the condensate drops from the bottom. So by playing with the ratio of the dropwise condensation and the filmwise condensation domains, we can try to optimize the efficiency of this system. So if you do that in terms of water condensate, how much water we condensed versus this filmwise condensation percentage, this is filmwise condensation versus the entire area, you see there's an optimal level in that particular case. For case one, this is a different case, 20 degrees centigrade ambient 80-degree relative humidity. And that's more like what we may have here in Chicago. And this 35 degrees C and 80% kind of conditions that you will get in, where you are every now and then. So, or more frequently than that. So here, what is important is in terms of the condensation efficiency, the collection, if you want to collect water from the atmosphere, you want to be at about 30 to 35% film-wise condensation area. If you go from that point on, it works against you. And this is the improvement compared to the area we have drop-wise condensation alone. So you get about 30 or 35%. And again, this is in the presence of non-condensable gases. So if you have something in a pure steam environment, these improvements would be much higher. In terms of heat transfer coefficient, again, about the same domain, film-wise condensation between 30 and 35, you're maximizing, you're going about 30 to 35% better heat transfer coefficient compared to just the drop-wise coefficient surface, which is your control surface. Liquid jet cooling, that's the third application I'm going to talk to you about. And it is a busy slide, but what I want to orient you here, I have a heater. We have a heater right under that metal plate. There are superhydrophilic areas. This is the wedges. We're showing 3 wedges here, by the way, and then superhydrophobic in the background. And for that particular case, the heaters range from about 10 to about 100 watts, and the area was about a 1 square centimeter. Now, what we do here is, you're looking down on this, but if you take this and you turn it in a way that now this path is underneath this plate, you can now have a liquid jet that strikes that plate. And because of this wettability confinement, the jet doesn't go all the way around. It just follows that wettable path. So the jet goes from here to here, it does not spill over. And then after it accumulates on this end right here, it drips. And what is going on there? It takes heat away from this heater. So this is a liquid jet chip cooling. The chip is, of course, here. And you have something that is in real time. You inject a liquid, and by doing this, you're taking heat away, and then that is dripped, and then, of course, you remove this. So how is that happening? Well, the incoming flow is coming from right to left. This is the hot domain right here, and you see as more and more fluid comes in, eventually this accumulates and drips down. When you do this, I'll show you the video here as it's seen on the side. This is where the jet is striking. The jet is moving from right to left. Again, this is, if you looked at it from the bottom up, you will see the triangular path. So this is a narrow path that gets wider and wider, and as you get more and more liquid here, eventually it drips off. The hot domain is right here, and that hot domain, of course, is kept cool by the fact that this liquid film is driving over it. Now, there are interesting things here related to a single versus multiple of those tracks. And when you look at, let's say, let me get my laser pointer back. When you look at the height of this film and the width of that film as it propagates from the narrow to the wide end right here, you can do simple heat transfer manipulations. And the heat transfer, of course, depends on Reynolds number and Prandtl number, and then the width of the film thickness right here, and then a constant. And then when you do this, and you, in fact, have 2 possibilities: a single track versus multiple tracks. I'll show them in a minute. The multiple track heat transfer coefficient is compared to the single track heat transfer coefficient, but there's also this multiplicative factors right here that can be quite a bit larger than 1. So if you play your cards right, this is the width, for example, of the single track, and how it applies, how it compares to the number of tracks multiplied by the width of the multiple tracks. so these are smaller tracks, then this ratio, you can make it, because remember, this is the width of the single track, and this is n times the width of multiple tracks, and these are multiple tracks are generally, this product here is smaller than that. So this is a larger than 1. And because of that exponent, this is a larger than 1 factor. Now, if you also compare the width of the single track to the width of the multiple tracks, this is much, much smaller than the single track. So that, again, this is larger than 1. So if you take these factors together, you have a coefficient here that is larger than 1, much larger than 1, and multiplies the heat transfer coefficient of a single track. That tells you that if you use multiple tracks, you have a much better chance of cooling the same spot with less liquid. And that's what I'm going to show you here. This is how you implement the cooling of this particular, let's say, hot spot. You have 2 jets that are coming in. These are the narrower tracks that we have, again, triangular, and you see the single track width is this. I'm sorry, the multiple track width is this. You see the red dot right here, that's another one up there, another one down there, and so on. We have 4 of them. Now, again, for the same reason that I showed earlier, because the heat transfer coefficient for these thinner films is so much higher, you get the benefit now of having to slow down the jet here, so you use less of the coolant. Okay, and I have some numbers here that indicates the number of tracks, how these widths and thicknesses compare with one another, and so on. Now, what is important here is, of course, to keep cool that hot spot. And for all practical purposes, the higher that curve is, this is a difference with another fixed temperature. The higher that curve is, the hotter your hot spot becomes. And you see here, the only curve that has multiple tracks, like one I showed you, has temperature of the hot spot that is considerably lower, 10 degrees or even more than that with a single track. So bottom line, when we do this, when we use this strategy of using multiple tracks to thin the film that passes over the hot spot, you get the benefit by having the hot spot here being at a lower temperature and at the same time using a lower amount of the coolant that is flowing. Okay, so vapor chamber heat spreader, that's the last example that I'm going to use. They are, of course, closed devices. And when you're looking at a heat spreader that is a slab, let's say, exaggerated slab, and you have a hot spot here, the conduction, let's say, field looks like this, and you have an isothermal, actually a non-isothermal heat injection at the top. The plate at the top is non-isothermal, and of course that changes the rejection rate accordingly. And that's something generally when you have non-uniformity of temperature on a plate, then you need more sophisticated ways of cooling it down. What the, let's say that the traditional vapor chamber does, it creates an isothermal region at the top. Compare this, which is non-isothermal, to this. And this is done by using wicks that, in fact, facilitate certain things. Remember, you have a liquid, let's say, in this closed chamber. That liquid is evaporating because of the heating from this hot spot. And these are the vapor molecules right here. These vapor molecules are moving up. They now have encountered the cool part, the condenser of the vapor chamber. And when that happens, they condense, of course, and then they recycle back through these wick posts. They're not, these are posts. So you do have communication of this chamber with this right here behind it, for example. And this is kind of a perpetuating process. The liquid from here, the condensate from here eventually gets returned to this and so on. But this kind of devices, the vapor chambers with these actually wicked structures, have some limits, capillary limits and so on. And what we wanted to do is actually try to eliminate those with wettability patterning. So instead of using these wicks that are limited by the speed that they can move the condensate and also the distance that they can move the condensate to, the velocity of the wettability pattern surfaces is bigger than that of the wick, and the length also that you can transport with the wettability patterns, the condensate is larger. So with these advantages, what did we do? Well, we put it to use, right? So we use now this type of surfaces where we have wettable in a non-wettable background to move the condensate in a vapor chamber very quickly. Now, this is the principle, of course, that I showed you earlier, the principle of using this wettability pattern to move the liquid from the dropwise condensation to the film-wise condensation and then away from there. And this is the principle that we use on the condenser of the vapor chamber. So in practice, you have, this is how the vapor chamber condenser looks like. You see how these ribs are implemented and how the liquid now is formed, is actually accumulating at these pools. And when you do that, you now have the ability to bridge to the other side. So this is now how the vapor chamber works. This is the evaporator for a single hot spot in the middle. You have the evaporation from here. Black indicates wettable, shiny indicates non-wettable, not super non-wettable, but just non-wettable, dropwise condensation. And when this happens, this is actually the evaporator. You evaporate from here the condenser, which is facing down. This is kind of an open, like a toaster open, you know, a kitchen toaster, right? That you've opened in a way that you see how those two mate with each other. This is the condenser. I'm sorry. Let me again get my pointer. This is the condenser. This is the evaporator. The evaporator is depicted here in reality, and the condenser is depicted here in reality. But when you imagine this, you hold that hinge, and then you lower this down, and that closes that vapor chamber. And now you see the evaporation occurring from the hot spot right here. It goes, the vapor goes and condenses, and then because of these patterns, it actually accumulates at those pool areas and so on. And after it becomes big enough, it bridges and it connects now with this star ribs right here, and the condensate returns to the circle. And that process is perpetuated. So that's what I said earlier. The heater eventually heats up and evaporates the liquid. The liquid condenses on the other side at specific domains, these pools that I showed you here. And then when they become big enough, this accumulated fluids there, the volumes, they bridge, and the whole thing happens again and again. So how important is this? Well, it's quite important from the sense that you have the thermal resistance, and that's a critical quantitative, let's say, metric to measure one against the other. This is how a fully wicked line vapor chamber looks like with the post right here. And this is the condenser, this is the evaporator. And when you have this wick-free, totally wick-free vapor chamber that you have no wicks at all, and liquids are moving much, much faster in there because of this wedge pattern and Laplace pressure type of influence, you see how the wick-free vapor chamber has a substantially lower thermal resistance than the conventional fully wick-lined vapor chamber. These are not the best values, neither for the wicked lined chamber nor for our wick-free chamber, but the trend is maintained. So what you've done here is actually created a device that can enhance, create a the new level of technology for vapor chamber heat spreaders. They also, these spreaders also behave in the thermal diodes, but I'm not going to go into this. This is benchmarking how good are our devices. You want to have them small enough and with high enough power. This, I don't know if you can see it, this is the effective length, the lower, the better. So we're pretty good. This is the UIC technology compared to some others, GE, UCLA, University of Colorado, Raytheon, and so on. This is, of course, to be fair here, these are data from 2015, and these are data more recently from us. But just as a benchmark, the scales that we are dealing are quite small, and then the powers that we can handle, the red here is the power. This is the heat flux, for example, here. That's the one that is, again, quite competitive. You see it's among the highest. This is the highest, of course, and that appears to be the smallest, which is the greatest, and the highest power. That's also the greatest from all those, but we're pretty competitive. Now, when it comes to the benchmarking against power versus thermal resistance, you want to have the lowest thermal resistance as possible, and that's thermal resistance, the blue diamond right here, and the power, this needs to be as high as possible, the red bar. So again, we're pretty competitive compared to other technologies. So I don't want to be spending much more time on this. What I think is important to summarize here, I gave you a summary of how fluid surface interactions are ubiquitous in practice and technologies that range from microfluidics to heat transfer. I also presented some applications of surface wettability engineering, which is really very well suited for managing liquid transport in applications that range from, microfluidic devices to condensers, vapor chamber heat spreaders, fuel cells, environmental sensors, liquid, oil, water separators, and so on. And then, of course, and that's the reason, of course, that you have created the group there, challenges abound. There's so many of them, and it's so critical that actually limit the technology that, a center of that, a group of that sort is an excellent choice, I think, for a young group of academics in a very dynamic institution. So acknowledgement as I wrap up my talk, I had the benefit and the privilege to have many people from all corners of the world, and many of them from your country, and some of them are actually professors now in prominent schools. Manish is at UCL in London. We have Tom Schutz, used to be an assistant professor at the HI in Zurich, and others who are actually around US industry. And of course, postdocs and visitors, Professor Ranjan Ganguly, who's in the audience, a great friend and colleague. Palab, of course, Mahapatra, who's a professor there. And again, a great colleague who is quite a bit younger than me, but one of the brilliant minds that passed through my lab here. And Shavik Chatterjee and Tamal Roy, who's now in Switzerland, Dr. Poulikakis' group. And of course, I wouldn't be fair unless I listed the funders of this work, the Office of Naval Research here in the United States, the National Science Foundation, the premier institution, actually foundation that funds basic research in the US, NASA over the years, a small company in Boston, and the Non-Woven's Institute in North Carolina. And having that, I'll show an old favorite that Ranjan had fun putting together with Jared when he visited for his sabbatical 10 years ago. So thank you very much. I'll stop sharing, and I'll be very happy to engage in a discussion with you.
Thank you, Professor. I think there is one question asked by one student, Krismadas.
Yes. Is there a range for the drop? I can read it. Yes. Is there a range for the droplet size which can be drained for efficient dropwise condensation? Yes. In principle, you want to keep the characteristic length of these patterns, and of course, the droplet size smaller than the capillary length. For water at room temperature, that is about 2.7 millimeters. As you raise the temperature, that's going to be smaller than that. For other liquids, it depends what is how low is the surface tension. The surface tension, remember, designates the capillary length, and that is something that the lower the surface tension, the lower the capillary length. So it depends on the fluid. That's my answer. And you can find that capillary length for any fluid, and that will be the highest length scale for droplets that you can manipulate with the technology of this type that I showed you. Now, Indad Chaudhuri is asking, I'm expecting the wedge-shaped wettability pattern for low surface tension liquid transport can be used for open surface oil-water emulsion creation. Can you please comment on that? Well, emulsion, remember, you have to suspend one liquid into another. So, Imdad, if you use the technology that I showed you, the liquid would be stuck to the surface. So, for emulsion, you need a way to detach from the solid surface. So I don't see any quick. I may be missing something here about what you had in mind, but I'll be happy to, to discuss that with you outside that. But in principle, remember, our liquids stay in contact with the surfaces. Now, Dr. Raghuraman says, wettability and surface tension in fuel cells. Can you explain that for us? Yes. In fuel cells, right, you have liquids and you have gases. And of course, you want to be able to have them both work in sync. Remember, if the bubble, the gas, sticks on the surface where the catalysis is happening, you're not going to have the liquid to contact that area. So there are management issues that have to do with keeping the liquid where you want it and keep the gas where you want it. And when you have, for example, a surface that you want the liquid to be on and it's clogged by the bubbles, or the other way around, right? You have the bubbles or the liquid not allowing the gas to touch a porous surface and pass through to the other side. These are the type of fluid management issues that are very related to this type of technologies, fuel cells, and so on. So the management aspect of bubbles and liquids, that's the critical point. So bubbles are more important than droplets there. Now, I see another picture, actually another professor, I'm sorry, another question. Did the extent of mixing change with the change in position of the hydrophobic patch of the experiment with 2 microchannels merging to 1? Absolutely, yes, Venkatesh, because we placed that island at a point where we thought that it will do the best job in creating this wake. And we moved it around, and we saw that the position I showed you was not the optimal, not the absolute optimal, but it was a very good position to create not a lot of constriction to the liquid around, but also create the wake mixing that you wanted. So absolutely, you're right about what you say. The mixing changed with what we placed the island, and also what the shape the island was. That's another important application. Manoj says, in case of vapor chamber with pattern condenser, will it work for any orientation? And also, okay, let's answer that first. If you are staying below the capillary length, remember, gravity does not play a role. But gravity would play a role when you accumulate quite a bit of water, and now you have volumes that are, with characteristic lengths more than 2 millimeters or so. And in principle, we found that at some configurations with the pattern, if you had the vapor chamber horizontal or vertical, there was from one point on a difference. And of course, the vertical was affected by gravity more than the horizontal. So yes, gravity can play a role, but in principle, if you design the system right, these systems would work even in the absence of gravity. You don't need gravity to drive the condensate back in space, for example. That was the first question. And also, can it be effective in case of mobile application where a lot of vibration is present? And yes, the thing though is that vibration and orientation is important, of course. But the smaller you make those chambers, remember the capillary forces are dominant, right? So it's all a balance between, if the characteristic length, for example, of the meniscus, let's say in the vapor chamber, is of the order of a fraction of a millimeter. Remember, you have sigma over r as the capillary pressure, and that can be quite big. Now, of course, if you take the phone and you slam it and you have 10 Gs or 15 Gs, that would eventually redistribute the liquid, but it doesn't mean that you cannot restart the process, because remember what happens is the liquid gets into the vapor phase, the vapor condenses, and then the whole thing happens. So even if you, let's say the 10 Gs or 15 strike that you gave to your phone when you dropped it, kind of created all the liquid to go on one side and pull on one side, remember all that stuff would redistribute, because now you're going to have a hot thing vaporizing some of the liquid, and then the whole thing will restart. So a very quick question: does the residual of the droplet in the moving path resist the movement of the next drop? Actually, what happens is the droplet through the Laplace pressure distributes and occupies as much as it can, and it is continuous. So it keeps going, because as long as you have curvature, that droplet doesn't want to stay as a bulge. It pushes towards the wide end. If you have some kind of an obstacle there, of course, that would be an issue. But as long as you have a droplet, even if you have the new droplet come to it, eventually the Laplace pressure will drain it, of course with some type of delay. If yes, then how can it be used for continuous cooling? As I said, as I showed you also in the video, these wedges keep pumping. It doesn't matter how much liquid you put on them. They will keep pumping up to the point, to their capacity, that they have drained the fluid to the other side. If you overwhelm it, of course, then wettability patterning would not do much, right? It's all about relative. Wettability patterning has to be to the scale of the liquid volumes that you have. Now, Krishnadas says, could you please comment on the challenges of fabricating this wettable surfaces and effectiveness over other techniques? Everything that we make has to be low cost, because if we make something that is extremely expensive, then it's not viable economically. So all of the surfaces that we have, and Palab knows that very well, are pretty much sprayed and then patterned, either with exposure to laser, and we're talking about laser, not sophisticated lasers. I'm talking about CO2 lasers, the marking lasers, and so on. So all of the patterns that we use and we apply are done with chemicals that are out there, with the exception of the POS compound that is coming from the Air Force, the US Air Force. And they're done with patterning these shapes with either masking is not a very efficient way. It's more expensive and it's tedious. But with the laser marking, you have quite a bit of throughput, and it's very viable. So soft lithography would not work for above. It would work, but it would be expensive. That's basically it. And I think I went through the discussions.
Yes, I think we have exhausted all the questions, but if there is any other questions, we can
yeah, you can unmute yourselves and ask me anything. I mean, we're here to just share ideas, and please don't hold back. There's no question that does not have a foundation, and there may be a question that is actually drawn from what I did not cover well. So feel free to ask anything.
Professor, I have one question. I am Manoj. Actually, if we compare the cost of the condenser designed with patterned and drop wedge condensation with the cost of the condenser with designed with film condensation, so how much is the order of magnitude difference is there in their cost if we take approximately 50 centimeter cross 50 centimeter of the area?
Right, and that's a good question, because if your vapor chamber is one for a cell phone, it would be small. It will be then, in that sense, when it comes to scalability, it's not a big issue. But if you want to make something, let's say that you want to create a vapor chamber like that for a diode to be in a building, right? In a building, in the sense that it creates a diode as a wall for a green building and so on, then you're talking about a much larger system. So the laser patterning, for example, would be no problem at all for the cellular phone, device. But if you have the laser patterning for a slab that is, 5 meters by well, not 5 meters, maybe smaller, let's say 3 meters by 5 meters, that would be an issue with an engraver, right? And the laser engraver. So it all depends. If it is something that is construction that is very big, then scalability becomes an issue and cost. But if it's something that of the order of let's say a power board, these are very easily done and inexpensively done with these laser patterning systems, laser engraving systems. Any kind of machine shop has one of them. These are the same lasers that people have when they go and they engrave a plaque, an award and all that stuff, and they're everywhere. CO2 lasers that can put quite a bit of power at the spot. And what they do, they just burn everything up at the point of application.
Excuse me, Professor, I have a question. This regarding the wickless and wick you had shown in there. Now, relate to the wick and wick heat pipes also, it is similar to that?
Yeah, the heat pipes are effectively taking the heat from one side of the long device and bring it to the other side. Vapor chambers are very good at bringing the heat from one side to the other that is opposing, but they are effectively the same type of thermodynamic system. It's a closed system where you vaporize your fluid, you condense it, and then you bring it back. So they are operating on the same type of cycle. Yeah.
Correct.
Anybody else?
Questions? Any comments?
Sir, I had a question, sir.
Yes, go ahead.
Sir, in your liquid jet chip cooling, sir, how did you prevent, there was a nozzle, right? So how did you force the whole of the liquid that was coming from the nozzle to go into that? Means, was there any splashing, or how did you control the velocity to such small ranges?
Right, very good question. If of course you have a needle that injects fluid with tremendous velocity, you'll splash, right? So what we did is we balanced it. We started with a liquid rising but not reaching the plate, and eventually pushing the flow rate higher and higher until it reached the plate. So it was a laminar jet that did not have enough momentum to actually veer away from the start of the wedge plate, of the wedge track. So of course, and in fact, what we did sometimes, we even angled the jet to be against the track, and it's still, the fluid turned more than 90 degrees to go back along the track. So again, as I said, good question. We just used velocities of ejection from the needle to be in the laminar regime, and when they touch the start of the wedge track, they actually just very nicely laminarly turn around. But if you push it harder, of course it's going to splash. Yes, there's a limit to how fast you can push that. So there's a limit of the capacity in terms of the rate that you can use with this specific system.
Thank you, sir.
There is something that I could tell you that has to do with some videos that are put up by the National Science Foundation, and this is let me see if I can It's a very popular video, and I'll give you the link, and it's right here. I'm just going to put it in the chat. For those of you who are curious, you can go ahead and so let me do this. I'll give you the link in the chat. Take just a second. This is the video that the National Science Foundation has put together based on a lot of the things that you saw today from our work. And there are also two other groups, one from MIT, Kripa Varanasi's group at MIT, and also another group from Utah. And it's fun to watch. So we actually, the video has been viewed about 200,000 times. So it became viral at one point, which was nice to see, you know, for academics to see something being viewed by people out there who do not quite, you know the science and engineering behind it.
Any
so
other
Palab,
questions?
I can stay on if you want to talk with me, with some of your colleagues. Actually, it would be nice. If not, we can call it.
Yeah, Asis has left. He has some other works. We have another faculty, Siva, here. From here, I am seeing Manish Tiwari is also joined.
Hey, Manish.
Oh, hi, Prof. Good.
How are you doing, Prof? How are you doing?
I'm all right. I'm all right. Thank you.
So nice to see you, all of you, my academic children. You know, it's great to have you all, and it's thank God for Zoom, and thank God for the group.
Yeah, absolutely.
IIT Madras. Yeah.
I was just going to say that the only problem is that the children are losing hair before the parents, so that's the only problem with that. But it's great to see you. Thank you for that.
That's okay. There's nothing you can do about genetics, right? And inheritance and all that stuff. And sometimes our parents are kinder to some of us, and other parents are not as kind. But believe me, they mean the best for us, right? So, it's so nice to be able to do this. I appreciate, you know, the opportunity to exchange ideas. I'm so also happy to see that the group has done such a good job. I did go through the website they have, and I saw the examples. There's a lot of good work happening there, and you know, a lot of people who are doing great work, and I'm convinced that, you know, this group would do well, and it will be probably something to be proud about down the road, and it'll be great to see as we go on in the sunset, and see our academic children doing better and bigger than us, and that's what it's all about. We're so proud of all of you, and that's something that I will never stop saying. Yeah.
So we have Siva here.
Siva, hi, Siva.
Hello.
How are you?
Hello, Professor Constantine. Nice to meet you, although virtually. I really hope that soon we'll be able to even host you on campus here, and please do visit us. We are all upcoming groups. I don't quite myself work in a lot of fluidics, but I'm sort of getting into collaborations with colleagues like Pallab and Ashish. I basically work with femtosecond lasers and just working with these, with fairly intense pulses. So I've been ionizing matter and material, and I found on the way that there's some really fascinating work that goes on with ultra-short pulse-based material processing and surface processing, and even inducing super hydrophobicity or hydrophilicity and controlling wettability and so on. So this got us sort of thinking and going into this area of work. We just have started doing a few little experiments, but I'm more like almost like the machine shop guy, although on micrometer sized textures or structures. So something we're getting into. I was intrigued by your talk more than anything else, rather than be able to ask you deep technical questions. The plethora of possibilities was tremendous, and it motivates us significantly to delve more into this area. So that's great, and we'd be happy to really continue benefiting from your expertise and some of the aspects that you motivated in terms of the flow without really digging up the channel and these applications. That's tremendous, and I'll take the liberty of getting in touch with you, especially in this regard, Professor.
Yeah, and Siva, so nice of you. And there is a lot of work that is happening right now, and I'm involved in this with a group in Nebraska. My colleagues there are using femtosecond lasers to do this at a far more accurate way and scalable way than a CO2 laser would allow you to do. And there's also, there's some nice groups in China that are doing excellent work in this laser surface interactions. And of course, there's, other work that has happened in the past with particles and so on, and lasers, right? Kostas Grigoropoulos at Berkeley has done some tremendous work in that area. But when it comes to areas, surface areas and lasers as a means of scaling up this functionalization of surfaces, there is a lot of promise. And your area, since it fits so well, I think it will be a great asset to the group there. You need people from exactly that area that know exactly how to manipulate really laser radiation as a means of creating structures that are not only physically but also chemically modified. And these are the kind of things that are just fascinating. Highly non-equilibrium, way off equilibrium processes happening in a minute fraction of a second with chemistry, fluid mechanics. I mean, it gets as tough as you can imagine to do all these. And we need all the help we can do. I mean, we can get from, science around the world to be able to understand that to the point where it becomes a technology that you can now create a large surface with a small fraction of the cost of what it costs today to make these surfaces.
Yeah, so indeed, it's very nice in that sense to have had a colloquium. I'll be in touch with you, of course, in combination with colleagues over here and possibly other places in India, like Manish maybe, so that we have a little community, some of us learning, optimizing, and probably when getting some expertise on the application and materials processing, functionalization of surfaces and so on. Others really applying it to more deeper fluidic science. Really, I really look forward to that. And someone with your experience would be ideal for sort of maybe like mentoring and curating our ideas. And as we go along as an expert colleague, I really look forward to that.
No, I look forward to it too. And I don't know how many of my students are attending the talk. They're a great resource. They are very happy to have them in the lab, and they're doing the work, of course, and they're teaching me a lot of things. And yeah, we can even have students communicate with one another and cross-pollinate in this area. That this is, and sometimes short visits.
Yes,
Shiva, because you send somebody out here for about 2 months, they'll come back with a lot of know-how and expertise, and that's something that is very valuable.
Yeah, actually, Professor, we have a plan of doing that. In the group, we have, like, due to the COVID, all the travel was restricted, but probably from next year we can do that. So we already have some plans. Maybe I'll discuss with you.
Yeah, and there are other things also I didn't show you. We're doing a lot of things also with sensing of the environment for biological compounds. There are other things that I've participated with Petros Koumoutsakos, who's at Harvard, on the molecular dynamic simulations. And I know that there are people there in your group who are doing molecular dynamic simulations, and there's a lot of stuff that there's a lot of overlap, and that would be great to be talking. I mean, the minimum we can do, even once a month, why not, right? I mean, if we can do that I spend 1 hour with you, I'll be happy to do that. Really, it's this kind of forums that create new ideas and get things going and put urgency in what we do, and that's something that can be tremendous when it comes to really moving at a speed that makes it worthwhile for industry to put money in and really start thinking about technologies and devices and manufacturing and all that stuff. Yeah.
Yeah.
Yes, indeed. Thank you. That's very motivating. And thank you, Pallab, for organizing this nice talk.
Well, you're
Thank
welcome.
Okay,
So I see there are a lot of people who are still here, so feel free. That's your last call. If you want to unmute yourselves and ask a question, I'm here, and I'll be happy to answer it.
Hi, Professor. This is Indar. So a little while ago, actually, I asked that question in the chat box also, that regarding that emulsification, open surface emulsification. So like, but I was expecting like you showed two cases. One is with a wedge track which transport a loss of extension liquid, and another case also you showed for open surface kind of micro mixture. So you are using two wedges and two liquids are coming and mixing. So what I was thinking, like, can we do like say one wedge track for low surface tension liquid transport and another wedge track for water transport, and in the mixing zone, like kind of whether we are able to do some kind of emulsion. I see.
Yeah, I get it. It's a good idea, but I'll tell you why I think it's not going to work. First of all, for this mixing problems, you got to have miscible media, right? Fluids.
Yes.
Oil and water do not mix, and when they mix in the emulsions, they require quite a bit of energy. I don't think that by mixing a droplet of water and a droplet of oil, you can create the emulsion that you have in mind. There's not enough energy there to be able to do that. And that's why I'm kind of skeptical about the feasibility of creating this process to create emulsions. There are a lot of other ways to create emulsions. And of course, depends what kind of suspended droplets you want to have in there, how small they are they nano, are they micro, what scale, and so on. When it comes to micro and nano, you're not going to be able to do that with this kind of millimeter scale devices that we use. So it's sometimes I think ideas come out of the blue, and I've thought about it quite a bit about emulsions, because other people have mentioned it, but I have not still kind of grasped a configuration where energetically this will be possible.
Okay, but whether is it possible by using some kind of roughness, like more roughness on the mixing area where mixing is happening, so that some kind of micron size or nanometer size oil or water droplet forms because of those roughness?
Yeah, I mean, it's again an issue of energetics. If you have one liquid sticking to this asperities, to these roughnesses and so on, then how do you take it off from there, right? I still cannot envision a system where I'll be able to consistently create small particles and disperse them in another liquid when these two liquids don't like each other, right? So
yes.
Yeah.
Okay.
Sir, I have a question.
Yeah.
So in the experiment where you put one drop in the middle and the liquid was getting distributed into 5 channels of hydrophilic channels. So by controlling the width of the hydrophilic strips or the wedge angle, and we quantitatively control the distribution of the volume of the liquid that we're dropping into each of the strips.
Yes, let me see if I can share that particular slide that you're talking about, the multiplexing slide, where we have one droplet that strikes a surface that is patterned, and that creates 5 other droplets, right? So this is the one. So remember, everything that winds up, let me get the laser pointer, everything that winds up at the edges of this tracks depends on how big is the droplet, how many tracks you have, right? And how long is the track itself. Because when you actually do the multiplexing, you have a volume of 1 splitting in 5. And as you see, with one droplet alone, you didn't reach the end, right? You got to wait quite a bit. With the second one, you go further and further. So if you had these spokes to be half size, then you could have done it with just one droplet. If you wanted to have, you know, in this particular case, I think you needed 3 droplets to be able to go all the way to the end. If the end, let's say, portions are the ones where you have the reagents that will do the colorimetric detection. So it depends on many things. As I said, size of the droplet, number of spokes, and the angle of the wedge and the length of the wedge. All those have to come together in a way that would allow you to do the measurements you want. But this is for statistical kind of measurements. You'd create multiple of the same, right? That's what you do.
Thank you, sir.
Oh, you're welcome. I think we need to wrap it up.
Yeah.
People are going. So.
Okay, thank you. Then thank you.
It was
all
a great talk.
Yeah.
Thank you.
Actually, it was my first talk that I attended, like that Professor Megaridis gave. So,
is that right?
Wonderful. Yeah, yeah. I haven't seen him presenting. It was such a lucid presentation.
You've seen the
and
students.
That's why...
You've seen the students and so on, and it's so fun to present one's work, and I mean, that's what we do. That's the only thing we have in life, right? I mean, that's what we do. We work and we produce things that a lot of people don't care about, right? So it's like when you have other people who appreciate it and enjoy it, it's even more enjoyable for us, like Ranjan. That's the point.
And Paulo, thanks a lot for arranging this. It was a wonderful session. Yeah.
Yeah. So I appreciate it. Thank you again. And I'm sure we'll be talking again soon, Paulo.
Sure. Yeah.
Okay. Have a great evening. And thanks for staying late.
Yeah.
Bye.
Thank you. Thank you, everyone, for attending.
Bye, everybody.
We'll close the session now. Bye. Harsa, you can stop the live now.